You know, we're constantly surrounded by this invisible world of information. Radio, Wi-Fi, 5G, all of it just flying right through the air around us. But how does it actually work? Well, the secret is this brilliant process, a kind of hidden language that makes it all possible. So today, we're going to decode that invisible language of the airwaves, signal modulation.
I mean, really think about it for a second. How does that song, that video, or that GPS signal travel from a transmitter miles away, through buildings and trees, and just arrive perfectly on your device? It sounds like straight up magic, right? But it's actually an incredibly clever piece of engineering that solves a really big problem.
So here's the thing. The original signals we want to send, like the sound waves of a song, are what we call low frequency. And to transmit a low frequency signal directly, you'd need an antenna that's about a quarter of the signal's wavelength. Well, for audio, that wavelength can be kilometers long, which means you'd need an impossibly ridiculously huge antenna. It's just not practical at all. So engineers needed a better way. And that better way, that ingenious solution that underpins pretty much all of our modern wireless communication, is signal modulation. You can think of it like this. Modulation is basically the art of piggybacking. We take our weak, low-frequency message signal, like your voice or a stream of data, and we impress it onto a strong, high-frequency signal we call a carrier wave. This carrier wave is powerful enough to travel long distances, and it effectively carries our information right along with it. Okay, so let's break this down into 4 super simple steps. First, you've got your message. Easy enough. Second, you generate a simple, boring, high-frequency carrier wave. Third, and this is the magic right here, you modulate. You change something about that carrier wave to match the pattern of your message. And finally, you transmit this new, powerful, encoded signal out into the world. You know, to really get a grip on this, we gotta go back to the beginning, to the analog originals that you probably use every single day without even thinking about it, AM and FM radio. Okay, but before we dive into AM and FM, there's one really important distinction we need to make. There are 2 main families of modulation. You've got analog modulation, which encodes a smooth, continuous wave, kind of like the sound of a voice. And then you have digital modulation, which encodes discrete little bits of info, the ones and zeros that make up all computer data. We're going to start with the classics, the analog methods. You know, the beautiful thing about these first methods is just how elegant and simple they are. With AM, or amplitude modulation, you just vary the height or the amplitude of that carrier wave to match your message. With FM, or frequency modulation, you keep the height the same, but you vary the speed or the frequency of the wave. Just 2 different approaches, both incredibly effective for broadcasting radio. But then, everything changed. Computers came along, and they needed to talk to each other. The problem was, they didn't speak in smooth, analog waves. Nope. They spoke in ones and zeros. And this is what sparked the digital revolution in modulation. And this quote right here, it just nails the new problem perfectly. The entire telephone network was built for the human voice, for analog tones. So how on earth could you send the sharp, distinct bits of computer data over a system that was designed for sound? Well, the answer came from a device many of us remember very well, the modem. So a modem, which by the way stands for modulator-demodulator, did this incredibly clever trick. It was basically a translator. It took sequences of digital bits from a computer and turned each one into a unique audible tone, which we call a symbol. It then literally played a melody of these tones over the phone line. The modem on the other end would just listen to that melody and translate it all back into the original ones and zeros. Pretty smart, right? So this whole process, this method of converting digital bits into specific changes in a carrier wave, that has a name. It's called keying, and it's the absolute foundation of all digital modulation. And you'll see right away how this builds on what we've already talked about. The basic digital methods are basically direct cousins of the analog ones. Amplitude shift keying, or ASK, is the digital version of AM. Frequency shift keying, or FSK, is the digital version of FM. And then we get a new one, phase shift keying, or PSK, which involves changing the starting point, or the phase, of the wave to represent data. Okay, so these basic keying methods were great for their time, but man, our hunger for data just exploded. We needed to send way more information way faster. And this is what pushed engineers to develop the truly incredible modulation techniques that power our modern wireless world. So the engineers started thinking, wait a minute, What if we don't just change one thing about the carrier wave? What if we could change two properties at the exact same time to pack in even more information?
And the answer to that question is QAM, or Quadrature Amplitude Modulation. It's this powerhouse hybrid that combines ASK and PSK. By changing both the amplitude and the phase of the carrier wave simultaneously, a single symbol can now represent a much larger sequence of bits. This was a massive leap in efficiency, and it's exactly why QAM is the engine driving everything from your HD cable TV to your Wi-Fi router and your 4G LTE connection.
But for the really heavy-duty stuff like 5G, we need something even more clever: OFDM. See, the problem with sending one super fast stream of data is that it's actually really fragile. One little blip of interference can mess up a huge chunk of information. OFDM's solution is brilliant: divide and conquer. It splits that one fast stream into thousands of much slower, parallel streams. Now, if one of those slow streams gets hit by interference, only a tiny piece of the total information is lost, and it's super easy to correct. This makes the whole signal incredibly robust and efficient, perfect for today's crowded airwaves. So when you step back and look at the whole picture, you see how this process of modulation has evolved from these simple analog waves into these incredibly complex digital schemes. It really is the unsung hero, working silently behind the scenes of almost every single piece of wireless tech we rely on. I mean, just think about your day. The radio in your car, your Bluetooth headphones, your Wi-Fi at home, the GPS in your phone, your 5G data connection, even satellite TV. None of it, absolutely none of it, would be possible without this fundamental principle of impressing information onto a carrier wave. It's truly one of the foundational technologies of our connected world. And all of this leaves us with a really fascinating question for the future. As we demand more and more and more data for things like virtual reality, autonomous cars, the Internet of Things, the airwaves are only going to get more crowded. So what comes after QAM and OFDM? What will be the next brilliant breakthrough in this invisible language of modulation?